Okay, let's start to implement particle swarm optimization in MATLAB. First of all, we need an optimization problem to solve using PSO. We choose a simple optimization problem. It's the minimization of the value of a function called a sphere. It is defined as f(sph) of x, where x is a vector in the Rn space. So x is a vector, and the value of function for x equals to summation of xi squared. I is from 1 to n, or simply it's the norm of x squared. This is the sphere function. It's a very simple function, and we know if the search space is Rn, the global minimum of this function is the origin, where all components of x equal to 0. We would like to implement PSO to solve this problem. However, this is for educational purpose, and we intentionally choose this simple problem to make the implementation of cost function as simple as possible and focus on the implementation of PSO itself. Okay, let's go to MATLAB and implement the cost function and then implement the PSO step by step using MATLAB programming language. Here we create a new function using the edit command. Let's undock this from the main window and create a function which returns a value named z, and the name of function is a sphere and the input is x. The definition of function is the summation of all components squared. So z equals to summation of x element-wise squared, and this finishes the implementation of the sphere function. So now we have an optimization problem. Okay, let's save it with the name of a sphere and create another file. This file, let's save it with name PSO, contains the implementation of particle swarm optimization. Firstly, we will implement this as a script. Then we'll convert it to a function which can be used to solve any kind of optimization problem. Okay, let's start this program with CLC, which clears the screen, the main window of MATLAB, clear, which clears the workspace, and we make sure that there is not any unneeded variables defined in the workspace, and close all, which closes all figure windows maybe previously created by MATLAB, and this makes sure that there is not any unnecessary figure windows opened in MATLAB. In general, implementation of meta-heuristics can be done in several sections. These sections have logical meanings and enable us to make a logical process of implementing meta-heuristics and make the code more readable. The first section is the problem definition. The next section is the parameters of the algorithm, parameters of PSO in this case. And the next section is the initialization section, which makes ready the algorithm to be started. And the next section is the iteration section and the main loop of algorithm, main loop of PSO. And the final section is the results section. These 5 sections contain all needed parts of the implementation of particle swarm optimization or any kind of meta-heuristic. If you see our implementations of other meta-heuristics shared on Yarpiz.com, you will see that all of them share these sections. Okay, let's start with the problem definition section. In this section, we are going to define the optimization problem which is being solved by PSO. The main component of the problem is the cost function in this case. It's an objective function that we'd like to minimize its value. So the cost function is defined as a function of x, which returns the sphere x. This helps us to refer to the cost function with a common phrase as cost function, and if in future we would like to change our cost function, for example to a function named myCost, just the line 7 is modified and the other parts of the program remain unchanged. Okay, let's change the cost function to sphere and continue with the definition of search space. Let's comment out this line with cost function. The number of variables denoted by n_var. How many decision variables or unknown variables exist in this problem? For example, in this case, we are searching in a 5-dimensional search space. So x is a vector in R5, a 5-dimensional space. So the number of decision variables is denoted by n_var, and this is the number of unknown or decision variables. The vectors containing solutions are matrices at all. The size of these matrices or vectors is defined by a variable named var size. So any position, any solution in the search space is a vector of size 1 row and n_var columns. So our solutions are horizontal vectors, not vertical vectors. A horizontal vector with 1 row and 5 columns in this case. So this is the matrix size of decision variables. Using tab, we align these comments for the neatness of code. Let's define the range of variables. We defined the cost function, the number of variables, and the definition of range for the decision variables remains. The minimum value of variables, varmin. In this case, we assume that the -10 is the minimum value of the variables. So we comment this line by lower bound of decision variables. And just like the lower bound, we define an upper bound to +10 as the upper bound of decision variables. All of 5 decision variables are real numbers from -10 to 10. So our search space is the 5-time Cartesian product of this range from -10 to 10 to itself. We are searching for a value in this range which minimizes this function, which is defined as cost function using this function handle notation in MATLAB. Okay, the problem definition section is finished. We defined the problem. Now, let's define the parameters of PSO. First of all, the PSO is an iterative algorithm. How many times the PSO will iterate? It's the maximum number of iterations. We define it with maxit. And the value for maxit is 100 for now. Maximum number of iterations. Also, the number of particles in the swarm, or the swarm size, or the population size, is defined by npop. This is the population size, or swarm size. Number of particles in this implementation is 15 for now. Population size, or swarm size. If it is needed, we can modify these values to reach a better performance for PSO. The other parameters of PSO are the inertia coefficient and the learning coefficients or acceleration coefficients C1 and C2, which are defined in these equations. So we need to define W, C1 and C2 as parameters of PSO. Okay, let's define them. W, the inertia coefficient, is 1, as stated in the standard versions of PSO. Inertia coefficient. And C1, it's the personal learning or personal acceleration coefficient. Acceleration coefficient for the cognitive term is 2, as stated in the standard PSO. It's the personal acceleration coefficient. And C2 is the social or global acceleration coefficient. It also equals to 2. So for now, it seems that we defined all of parameters for PSO. In the next section, we are going to implement any initialization processes needed to start the PSO. We'll need to create a population and initialize the position of particles and evaluate them and initialize the values of personal best and global best and some other initialization tasks needed to run the PSO correctly. We are going to store information and data for the particles in an array of structures. So every particle in the swarm is a structure. We need a template to store the information about a particle, and this template contains all the needed fields and structural components of the particle. Let's name it as empty particle. This is just a template. The empty particle has a position, currently empty. So our template contains a field named position. This is the position of particle in the search space. Currently empty. We will fill it with the appropriate value in the next steps. Empty particle also contains a velocity. And for now, it's empty too. Also, every particle, just like Alice and Bob in the simple example of depth measurement, every particle has its own measurement, its own performance index, its own cost value. So we add another field named cost. And again, the value is empty for this template. Also, every particle has its own personal best, its own memory of best experience from the beginning of algorithm up to now. Also, an empty particle has a personal best, and every best has a position, and of course, every best has a cost. So, the best field in the empty particle is a structure itself. So, we have a structure with 4 fields: position, velocity, cost, and best, where the best field itself has 2 fields, position and cost. This defines the position of particle, this defines the velocity of particle, this defines the cost function value evaluated at the position of the particle, and these 2 represent the personal best for this particle. But we need a population of 50 particles. So we need to proliferate, we need to copy, we need to repeat this template to achieve an array of empty particles named population. So we start with the particle as an array of empty particle. So using the function repmat, repeat matrix. This repeats everything in the MATLAB. As an example, let's start with the matrix A equal to 1, 2, 3, 4. If we would like to repeat A horizontally, we can use concatenation operators. If we'd like to repeat vertically, we can use this notation. And for repetition in 2 dimensions, we can use this notation. However, this is for repetition in limited number of rows or columns, for example, for 2, 3, or 4 repetitions. For large number of repetitions, we need to call the repmat. Repmat A, for example, repeat the A 4 times in rows or vertically and 3 times in columns or horizontally. This is the 12 repetitions of A. Repmat can repeat anything, and we will repeat the empty particle defined here in n pop rows and 1 column. So this is an array of empty particles, and if we'll run this program, we'll see that an array of 50 structures is created, and it is named particle, and it contains various fields: position, velocity, cost, and the best, which is a structure itself. And this array contains 50 elements. Okay, let's start to fill the empty fields in this population. We need for loop for I from 1 to n pop. And let's create particles. Let's set the position of particles by particle I. The ith particle position equals to. In the lack of any information about the optimization problem and search space, we use the uniform distribution. And using the unifRND, uniform random function, we can create positions starting from varmin as a lower bound and ending to varmax as an upper bound, and with the size of var size. This creates a random position in the search space. Okay, let's run it, and you will see that every particle has a position now in the search space defined by the varmin, varmax, and var size. Okay, let's evaluate this particle. We can comment these lines to make the program more readable. The particle template, create population array, and initialize population members. And in this line, we are going to generate random solution. We are going to generate a random solution in the search space and locate the particle I, the ith particle, in that location. Okay, let's evaluate this particle. Evaluation. The particle I dot cost equals to cost function evaluated at the particle I position. If we run this program by the run command or hitting the F5, we'll see that the particle 1 located here is evaluated to this value. And for now, the particle 3, the third particle, is the best one for now. Okay. For velocity, we start with 0 velocity. So initialize velocity and particle I dot velocity equals to zeros. It's a matrix with all elements equal to 0 with the size of var size. And for now, the only memory of particle I is its current location. So its best memory equals to its current location too. So we update the personal best of the particle to its current location. So particle I dot best dot position equal to particle I dot position. And the cost is also updated. The population is initialized. The value for position, velocity, cost, and the personal best is correctly set for every member of the swarm. Let's run the application and see the result. You'll see that for the first particle located here, the velocity equals to 0, and the cost equals to this value, and the best equals to the current location. Okay. However, for the global best, we'll need to compute the global best of the swarm from this very first iteration. Okay, let's initialize the global best, the global memory of the whole swarm, by defining a global best. Initialize global best. The global best does not exist before the population is initialized. So the global best cost equals to the worst value it can hold. In this case, for the minimization problems, this worst value is the infinity. If the problem is maximization of a profit function or an objective function, this worst value should be minus infinity. But for now, we use the infinity value, which is the global best before beginning of time. Before anything existed, the global best is not defined, and it holds the worst value. It holds the worst case. So in the competition with any kind of existence, that particle will win the competition. Okay, let's implement the competition process among the particles and the global best. Update global best. To update the global best, we are going to compare the personal best of particle I to the global best. If particle I.best.cost, that means the cost value of the best experience of the i's particle is better than or less than the global best dot cost. This means the personal best of i's particle is better than global best. So the global best is replaced by particle I dot best. So we replace the global best with particle I dot best. Okay, let's run the program and see the result. Particle I. You'll see that the particles are initialized, and the best one among these particles is this one, I think. It's the 17th particle with the cost value of 36.3, and if we write the global best and hit the enter, we'll see that the 17th particle with the cost value of 36.3 is the global best for now. We created a mechanism to update the global best according to the current position and current situation of whole swarm. This finishes the initialization process of the particle swarm optimization, and we can start to iterate in the main loop of particle swarm optimization. However, we'll need some extra information. For example, the best cost value at every iteration of the algorithm, which is not needed to run the algorithm. We need this information to be informed about the status of the algorithm on every iteration. Okay, so we define an array named best costs, an empty matrix which contains maxit rows and one column. This is an array to hold best cost value on each iteration. Okay, this finishes the initialization part of the algorithm, and we are ready to implement the main loop of particle swarm optimization. We define the problem, we define the values of parameters of PSO, and we initialize the population and initialize the global best and personal best of swarm, and we defined an array to hold the best cost values on each iteration. Okay, let's start to implement the main loop of algorithm. The main loop is a for loop which begins from the first iteration to the last iteration defined by maxit. This loop for this setting will iterate 100 times, and on every iteration we will do these calculations to update the position and velocity of particles, obeying these simple rules and these geometrical representation. So we will do this for every particle in the swarm, and this needs another for loop which begins from 1 to n pop. Okay, for ith particle in the current iteration, firstly we will need to update the value of velocity. Particle I dot velocity equals to the value of velocity, the previous value of velocity. For the simplicity, we remove the index of time. We don't need to store the value of velocity, position, and other things in various iterations. We just need one copy of velocity, position, and other values, other time-based values. Okay, the new velocity value equals to w times the old value of velocity, plus a random number, but for every element of the position vector. So we need a random vector with the size of var size, and the acceleration coefficient, and times to particle I dot best dot position, the position of best experience of the ith particle, minus particle I dot position, the current position of particle. However, this is a vector, and this is a vector of the same size, and we need to multiply these vectors element by element. So we use this notation. And in the next line, C2 for the social component times rand var size and an element-wise multiplication times global best dot position minus particle I dot position. This is the first equation of the PSO update rules. This updates the velocity of particle. In the next step, particle I dot position is updated. and the position of particle, the new position, equals to old position plus the new velocity. The velocity is updated, and this value is the new one. Okay, this finishes the job. We need to evaluate the current position and then compare the current position to the personal best previously stored in the memory of ice particle. So we evaluate the particle I.cost equals to cost function evaluated at the current position of this particle. To compare the best position of ice particle and current location, we need to compare the cost values. If the cost of ice particle is less than particle I.best.cost, the cost value of the best experience so far, then we need to update the best. So the best position equals to current position of particle, and the best cost also is updated. Otherwise, if this condition does not hold, there is no need to update the best experience of the particle. If you note, we have these two lines in the initialization phase of the algorithm, and because the best does not exist in the initialization step, there is no need to any comparison between the best and the current position of the particle I. Okay, if this particle can be better than its best, it's probable that it can be better than the global best. And we can copy these lines of codes and add it here to update the global best as well. Okay, let's comment out these lines to make the program more readable. Update velocity, update position, and evaluation, and update personal best, and update global best. The PSO is implemented. We finished the job. If we'd like to see more information about the progress of the algorithm, we store the best cost value on every iteration. So, store the best cost value and best costs on the iteration, on the current iteration, equals to global best.cost. And just for information, display iteration information, we will display the current situation of algorithm, and we begin with the iteration it and best cost equal to best costs it. And we know that these are numbers and should be out of the string and should be converted to the string using num2str function. And all of them should be concatenated to be a single string matrix. Okay, let's run the algorithm and we'll see the result. The result is not so good and it is not promising. It's not interesting. The problem is with the parameters of the algorithm and defining a damping parameter, which reduces the inertia coefficient while the algorithm iterates, makes the performance of the algorithm better. So we define another parameter, wdamp, equal to 0.99. It is the damping ratio of inertia weight or inertia coefficient. And at the end of iteration, damping inertia coefficient, we damp this by multiplying the W by wdamp. So W reduces while the algorithm goes on and iterates. Okay, let's run the algorithm. Okay, I mistyped value, made this error. And the result shows that the algorithm runs perfectly for now. Okay, let's increase the maximum number of iterations to 1000 and run the algorithm. And let's see the global best and the value of position. You'll see that it is almost near the origin of the search space. Okay. In the results part, let's create a new figure and plot the best costs with the line widths of 2, and let's label the x-axis as the iterations and y label as best cost. And if you run this section by hitting the Control Enter, you'll see that this is the convergence plot of the PSO. But for this problem, this kind of problem, maybe instead of plot function, it's better to use the semi-log y function to create the convergence plot, which is better to display the progress of the algorithm, which is exponentially converging to the origin. Okay, let's make visible the grids and see the results. You'll see that this algorithm converges to the origin as the algorithm goes further and further. We implemented the particle swarm optimization from scratch in MATLAB programming language, and this code can be used in various optimization problems and various applications by minor modifications. However, this code is not the best one, and this is for educational purpose only. And if you need to do a professional job with this code, you are needed to modify the code and add something extra to make it more powerful and more applicable.